There we go. Hello, Pamela.
Hey, how are you doing?
Good. And where are you now?
I am outside of Lisbon, Portugal, in one of the suburbs.
That's really cool. And you've been there. And so, what are you doing there?
I am here working with folks at Nucleo who work on the Global Hands-On Universe and the Galileo Teacher Training Program to find ways to integrate CosmoQuest into what they're doing to help get more people around the world using CosmoQuest.
So, no vacation, all work.
Well, there will be some evenings spent walking castles and things like that. So it will be full work days, but it will also be full evenings, and I will probably return home in August, tired and thinner for all of the work, but having accomplished a lot.
That is awesome. I'm getting some echo here. Hold on. There, killed it. All right. Cool. So, if anyone has no idea what they've stumbled into, we are going to be recording a live episode of Astronomy Cast. This is our weekly facts-based journey through the cosmos. So, this is going to be episode 312. We're going to go into the inverse square law and other what did you describe it?
Nonlinear.
Nonlinear relationships. Which sounds like a dating site or something. Are you looking for a nonlinear relationship? I don't know.
I no.
No, no. An exponential relationship. Right. So it's going to take us about 25 minutes to record the episode, and then we will wrap up, and then stick around and try to answer some questions. Although it is evening for Pamela, and she's hungry, so it better be really snappy questions. So if you've got some questions you want to ask, you've got some posts you want to make while we're recording the show, you can make your posts on the event page. Hopefully you're watching this there. If you're watching this over on YouTube, you can make a comment there. You can use Twitter, use the hashtag AstronomyCast, although the Hangout gadget we're using doesn't track that anymore. So,
Really?
yeah, so I have to I gotta look somewhere else now.
I can monitor Twitter.
Uh, Always
I
do.
like the Twitters.
Yeah. Okay, sure. Yeah. And then
Sorry for the motion, everyone.
you're actually not moving from my perspective, but
Okay.
um,
It has image stabilization built in because, yeah, it's moving. There. Okay. I'm done typing.
it,
We're stable again.
that's weird. Is the image stabilization just like paused you entirely?
Okay.
Yeah. Anyway. Okay, great. So, is there anything you wanted to announce, mention, exclaim,
Don't
complain?
eat in kebab pizzerias in Finland?
Bad tummy. Yeah, all right. I think we'll save that from the episode.
Okay.
Okay, great. Well, I'm gonna press record.
Okay. I should do the same thing, shouldn't I?
You know, it's like one of those things that we do maybe sometimes.
Okay. I have pressed record. It is recording. The levels look okay.
I am also recording. All right. Oh, I need my intro in front of me here. Hold on. Now I'm the one holding this
Sorry,
up.
Preston. And Preston, good luck working on your thesis. You have all of our hopes and cheers and chocolate wishes going towards you.
Aw. All right, here we go. Astronomy Cast, episode 312 for Monday, June 24th, 2013. The Inverse Square Law and Other Strangeness. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos. We help you understand not only what we know, but how we know what we know. My name is Fraser Kane. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. I'm almost as far as we've ever been apart doing an astronomy cast this week. Last week was further, but this week I'm in Lisbon while you're in Vancouver, so we're spanning the continents here.
We could drill a hole right through the Earth, and
No.
no, I think I'd be in the Indian Ocean if I drilled the hole through the Earth.
Yeah, I don't know where I'd come out.
Really? Um, You should figure that out. I think there's a website you can go and check out that is like your antipode of on the Earth to find out where it would be. Great. So yeah, so you're in Portugal, continuing your European vacation, workcation.
No,
Yeah, I know it's
no.
totally not a vacation. You're working.
Yeah, my European inflict CosmoQuest on people in other countries.
All right. So the European tour, the CosmoQuest European tour.
Yes, that I'll agree with.
All right, cool. And just I want to make one quick little promotion and mention, which is that every Sunday night we connect a bunch of telescopes into a live Google Plus Hangout and show you the night sky live in real time. We'll show you planets. We'll show you deep sky objects, clusters, the moon, the sun. Sometimes it's fun times, and we often will bring in PhD astronomers to explain this stuff. So if you've got cloudy skies and you don't know what to do with your Sunday evening, join us on Google Plus. We do it whenever it gets dark on the West Coast. Right now it's summertime, so that's 9 p.m. Pacific Daylight Time, and even later in the East. But it'll get better in the summer. So. All right.
It'll
So
get better in the winter.
it get better in the winter. It gets
For north.
for
It'll
north.
get
That's right.
better in the southern summer.
That's right. All right. So why don't we have insects the size of horses? Why do bubbles form spheres? Why does it take so much energy to broadcast to every single star in the universe? Let's take a look at some non-linear mathematical relationships and see how they impact your day-to-day life. All right. Now you threw this topic on the list. You had a plan, and this is not my topic, and so I am going to just grill you to get to the bottom of this. Right, so let's sort of set the stage here. When you're talking about nonlinear relationships, what are you talking about?
So most of the time we are used to thinking of things that if you double them, you end up with 4. If you triple them, you end up with 9. So the numbers in that case, that's not linear. Linear is if you increase this one by 1, this one increases by 1. You increase this one by 2, this one goes up by 2. So if you think about the difference between Johnny and Sally's ages, it will always be the same because they grow up at the same rate, and so the separation stays the same. And if you do a plot of Johnny's age versus Sally's age, there'll be a line that's straight.
And this is really the only kind
Plot
of
of those.
mathematical concept that our poor human brains are really able to grok
In general,
intuitively.
yes.
When you think about,
Yeah.
you know what I mean? I mean that we evolved, on the savannah, and if there's one more lion, we should bring one more hunter, right?
And in school we all learned the whole y equals mx plus b. There might be a slope to the line, but it's still a line. So it may be that you add 1 here and you add 2/3 here. If you add 2 here, you add 4/3 here. But it's still a linear relationship. So that's what we're used to is that straight line when you put the things on the 2 axes.
Right. Okay. And so, but I mean, the universe sure doesn't like to play by the rules, and doesn't like to play by our pathetic human concepts. It makes its own rules. So then, what are the other kinds of the nonlinear relationships that can be out there?
Well, so they basically come in polynomial form. This is where if I have my x value over here, so like how fast my car is going, versus how much gas goes into it. The gas going into it hopefully isn't a power law, but you can imagine that it's y squared, y cubed, y to the 4/3. Anytime x equals y to the something that's a power, that's a power law.
Right, and I think your gas analogy is a great one, right? Because you have the situation that the harder you push down on the pedal, you're not just using more fuel. You're using in many cases, the engine is actually going to require a multiplier of the fuel.
Right.
If you
And
run
that's
your
because the friction goes up, the heat goes up, it gets more difficult to accelerate for mechanical reasons. Yeah.
yeah, and harder, yeah, exactly, that friction, harder to push through the air resistance as you're driving down the highway until it becomes just like a brick wall of air.
Right, right.
Yeah.
So then the other class of relationships that we tend to have are logarithmic relationships. So these are things that are powers of 10 or inverse powers of 10, which is where you get a logarithm basically. Inverse isn't quite the right way to think of it, but it's a shorthand.
And this is where
So,
you've kind of pulled into my background, which is computer science, right? We deal with the logarithmic scales all the time.
right.
When you search or sort an algorithm if you're going to sort a bunch of numbers, that actually follows a logarithmic scale. So you can sort a million numbers. It's not a million times as hard as to sort, you know, one number or 1,000 numbers, right? Every time you go up, it actually follows this logarithmic curve. So it doesn't. What is it? Doubles every 10? How does the logarithmic function work?
So with 10 is a so 1 is to 0, 2 sorry, 0 is to 1, 1 is to 10, 2 is to 100, 3 is to 1,000.
Right, right. And so the point is that it's a way that if your numbers are going up in stupid amounts, you can kind
Yeah.
of flatten the curve down and show it in a much sort of reasonable way, as opposed to just this line that just goes straight up. You can
Yes,
really
exactly.
bring it down and show it in a little bit more of a reasonable way.
And what's interesting is how many biological things, or at least the two senses of most importance that we have, our ability to see and our ability to hear, both work on logarithmic scales. The sounds around us vary by powers of 10, not by linear relationships. So when you turn your dial up to 11, it's not 11 times louder, it's tens and tens and tens of times louder.
Right. And so it gets a lot louder, a lot more quickly. But at the same time, you've got this other problem in the case of that sound, right? Which is that the sound trying to expand outward from the speakers is hitting, I guess, what we call the inverse square law, right?
Right. So here's where we start to get into where do these things matter.
Yes.
And an inverse square law is a power law. It's just a power law with a negative sign in it. Um, if you have something that's radiating out, it has to basically radiate out over an entire surface. Sound coming out of a speaker, it's not laser beamed to your ear with all the power from the speaker focusing the sound on your eardrum. Instead, it's radiating around away in a sphere, and so the energy gets spread out over the surface of the sphere. And for every distance that it goes, the area proportionately goes up by the square. So take the energy, divide it by the area, and if the area is going up by the square, that means the energy per small area on that surface is going down by the square.
All right, now let's bring it home to astronomy, which is, I think what people are hoping to hear. So give us some examples then in astronomy where we deal with this power law, because I mean it feels very mathy, and I know a lot of people are starting, their eyes start to glaze over with the math, but this is core to a
Right.
lot of the calculations that astronomers have to do with gravity and light and brightness and luminosity and sound and earthquakes and all this kinds of stuff. It all follows this exact same system.
Right. I'd argue that earthquakes are probably more planetary science than astronomy, but let's tie it back down
Planetary
to
geologist, sure.
physics, astronomy, space science. So the most fundamental place that we worry about it in astronomy is light as it radiates away from a star has to fill this entire sphere of space. And fill the surface, not fill the inside. You can have a flash of light, and that's a shell that radiates away. So the apparent brightness of a star decreases by that power law, that square, the distance squared, as you get further and further away. So if I double my distance to a star, the star will appear 4 times fainter. If I triple my distance to a star, it will appear 9 times fainter. And so things get faint fast. And that's problematic when you're trying to look at things far away, just because it is this ever increasing thing that you're dealing with.
Yeah, I mean, when we think about the stars that we can see out in the sky at night, most of those stars are bright, like really bright stars, because in many cases they're mostly just far away. Things like Betelgeuse and Rigel, and they're just big bright stars, and that's what it takes to put out that much energy over such great distances.
And this is that square law again working in a different way. When you look at the Hertzsprung-Russell diagram, the color magnitude diagram that we talked about in a past episode, you see that the brightest stars are also physically the biggest stars, and this is because they have more surface area for the light to come out of. Our own sun in the future, it's going to cool down, it's going to become colder, but it's also going to become much, much larger. And that much, much larger star is going to be significantly more luminous, and it'll be visible from a much bigger distance. So bigger stars with more surface area goes as the square of the radius of the star. So you double the size of a star, you multiply by 4 the surface area that's giving off light, and you end up with a much brighter star. There's other factors that have to do with temperature and stuff like that, but the basic idea holds.
Right, and people don't realize, like Betelgeuse, even though it's a gigantic star, would envelop Jupiter, it's actually cooler than the sun, the
Yeah,
surface.
yeah. It would still kill you quite effectively.
Oh, sure.
But
Yeah, no, absolutely. Okay, so that's a good example, right? And I think that exact same thing, it sort of comes back to this concept of searching for extraterrestrials, right? That if you were attempting to broadcast a signal out into space, to reach any distance, you're going to require a ton of power.
right. And this is one of those things, if you've ever walked too far away from your Wi-Fi antenna at home, you know how quickly you go from 5 bars to 0 on your laptop. Well, think about how quickly you go from detectable to not detectable as you move away from the planet Earth. Yeah, we sent episodes of I Love Lucy. Yes, we sent the opening games in the opening of the games in Germany from the Olympics with Hitler into outer space. But those signals are so amazingly weak that they're going to be very quickly imperceptible against the background noise of the universe. So trying to detect aliens from radio signals, the only way we could probably ever succeed is if they were purposely beaming a message into space and we just happened to look the right place at the exact right time.
So you actually think that the power requirements are so high that it would take an alien beaming a signal directly at us? Like it would require, I mean, I guess when you
For
think about it, like there are red dwarf stars that are 10 light years away from us that you require, a really powerful telescope to even discern them.
right,
And that's
and
the whole
and
power of a star.
right. So how are we going to pick up the accidentally leaked into the atmosphere television signals? I mean, at best, we might pick up the type of signal that's being sent to one of their own spacecraft somewhere else in their solar system. But even then, we just use enough energy for Voyager to pick it up when we send messages to Voyager. We're not trying to reach Alpha Centauri or anything else out there.
Yeah, yeah. Okay, so then now what about gravity? How does gravity sort of follow a similar role?
Well, gravity goes as the radius of the planet squared, but inversely again. So if you have a planet of a given mass, as that mass is held constant, so you assume the same mass all the time, and you make the planet bigger and bigger and bigger, the gravity you feel while standing on its surface goes down as the square of that radius again. So it works the same way as light.
Hmm.
So just like the light gets, you double the radius, the light goes down by a fourth. You double the radius of a planet, a gravity goes down by a fourth. Now the thing is, you're fundamentally changing a planet when you take a rocky planet and you try and blow it up with some unknown weightless nothing. Um, but at the same time, one interesting thing about this is you can end up with different combinations of mass and radius that lead to the same surface gravity. So if you try to stand on the surface of Saturn, which is so not dense it would float on water, it has almost the same surface gravity as Earth. So you would weigh almost the same amount on the surface of Saturn. So even though Saturn's this monstrously huge planet, because its mass is spread out over such a large volume, and that's the key. Volume goes up as a power of 3. So this is the insects the size of horses don't exist example you tried to give at the beginning. Um, if I have a sphere of material and I double its radius, its surface area goes up by a factor of 4, and its volume goes up by a factor of 8, which is the cube of that 2. So 2 times 2 times 2 is 8. So you're getting massive very quickly. This is the reason that someone who's twice as tall may weigh 8 times as much, which is kind of creepy to think about.
Right. Well, I mean, the we talk about those super Earths sometimes. You know how a planet has been found with twice the mass of the Earth, and you would think that if you were standing on the surface, as you mentioned before, that you would experience twice the gravity, but actually you would. It all just depends on the size of it correspondingly, right?
Yeah,
Is it
and
is
we're
it a
still
bigger planet?
figuring
Is it a
those things
smaller
out.
planet? Yeah, because we only get those measurements through either the radial velocity, so we only can detect their mass. We can't detect their size.
Exactly.
Yeah, right. So I definitely want to talk about that bug example here, right? So as your bug increases in volume, right, in
Yes.
size, in volume, it has to be correspondingly stronger. And that's what you're
And
mentioning. Go ahead.
and this is where the legs very quickly no longer become strong enough to hold it up. If you look at the radius of the legs on a bug, they have these hair-sized legs until you start looking at tarantulas, which finally have legs more like matchsticks or French fries. And those little tiny legs are able to hold up the bugs because they're small. They don't have that much volume. They don't have to hold that much stuff inside of them. Um, as you start to get to birds, which are another very lightweight animal, you see that the legs get a little bit bigger. As you start to get to small mammals, you have legs that are proportionately a little bit bigger compared to the body. Humans next, but then when you get to elephants, you suddenly have these, compared to the size of the body, these massively large radius legs. And that increase in the radius of the skeletal bones in the legs is needed to support that that power of 3 increase in the volume as the animals get bigger and bigger and bigger.
Right, dinosaurs and so on. Was it the California redwoods are pretty much at the largest size you can get for trees. Just that they can't pull water anymore up to the
Yeah,
top. If you got any bigger, they just the hydrostatic system they use to bring water out just doesn't work anymore, and there's no
yeah,
sort of bigger possible tree. So nature has tested that. And the other example I used in my introduction, right, with a balloon, thing I love about a balloon or like a bubble when you blow a bubble is you're seeing the math made for you right there. You get this bubble, you know what the radius of the bubble is because you can see it, and you can see the size and surface area and the volume of the bubble, and it's following this exact same rules. It's trying to match its volume versus its surface area to the minimum size.
right. So the most stuff that you can fit within a given surface area is fit inside of a sphere. Something like a pyramid is an extremely um, inefficient shape where the surface amount of surface area you have is greater than necessary to contain the volume.
So, what are some other situations in space, maybe, in astronomy, where we're going to see the same relationship play out? What do astronomers need to deal with, or even spacecraft engineers need to deal with as they're sending probes out to other places to be able to communicate with them, to, some of their trajectories, some of the gravitational flybys, things like that?
Well, as we look at all of the different orbital mechanics equations, there's always a to the power of the square root, there's a cube, a square. So just looking at Kepler's equations, we have the period, the amount of time that it takes an object to go around its central mass squared is proportional to its semi-major axis distance. You take the ellipse, you cut it in half on the long side, you measure that length, is equivalent to that semi-major axis cubed. So here you have one thing that's squared related to something else that's cubed, now plot. And so you end up with some fabulous curves. And what's awesome is if you're ever digging through an old professor's drawers, finding the fancy curve devices they had to try and draw all of these old plots back in the days when you had to turn in hand-drawn plots to journals.
Really?
Yeah, yeah.
What did one of these things look like?
Well, they just have on them the various, here's a square, here's a cube, and so they have these tightening cubes that represent the tightening curves, rather, that represent the different mathematical relationships. So you found the part that you needed and fitted it to the points on your paper.
Like a spirograph, kind of?
No, the spirographs were the things you did this with. You had the circle that you put inside the other circle with a gear, and you made flowers basically. No, this was like a stencil that you might use to draw circles today, except part of the stencil was it had these curves, and then you'd have to figure out where on this tightening curve the particular curve you needed happened to fall.
It's like finding an old slide rule.
Yeah,
Do
yeah.
you know how to use the slide rule?
No, no clue.
No.
Someone showed me once when I was in the 11th grade, and I knew how to do it for about a week and then forgot.
I think another good example of this situation is, for example, people always talk about the planets, astrology, and they talk about how the planets are aligning and it's going to have some nonsense effect on you. But the reality is that, you're experiencing a zillion, I believe is the right math, times more from just the gravity of the Earth and the Moon, but even that's not very
Well,
much. You're feeling more gravity from mountains, right? Because the
and
distances.
the more important thing is if you calculate the mass of a semi truck driving past you, or not the mass, if you calculate the gravitational pull of an average massed semi truck driving past you, its pull on you as it drives past is going to be greater than that of any of the planets outside of Earth.
Yeah.
So, if unless you're plotting the movements of the local fleet of shipping trucks and trains, I don't think you can correctly compensate for their effects relative to all of the other planets.
Yeah, it's like the tides, right? The majority of the tides comes from the moon, not the sun, even though the moon is, it's just because the moon is closer, even though the sun
Yeah,
has much, much more mass than the moon. It's just that the moon is closer, and so we experience more
yeah,
gravitational effect from it.
yeah.
Cool. Okay, well, thank you very much, Pamela.
It's my pleasure. Thank you.
Stop. Save.
Okay.
Don't go anywhere.
I'm trying not to, although I may be occasionally rotating my screen.
Not you. I'm talking about the people who are watching this.
Okay. Clearly, I'm
Yeah.
tired and hungry.
Tired and hungry. Yeah. Too bad. All right, let me see. So Michael Jobin says when you co-phase two 5 dB antennas, you don't get 10 dB, you get 7.5 dB. So I think that's a great example.
Yeah.
Um, Welcome to Europe, Pamela. Could you guys do an episode about Jupiter's moon, Callisto, and Ganymede? Maybe adding some information on the most recent plans of ESA and NASA to send probes and missions. So we did an episode about Jupiter's moons. This comes from Calendorian. We did an episode about Jupiter's moons in the 50s somewhere, 55, 56, I think. We
Not the
covered
1950s, the
in
50
the
episode-ish.
1950s. We've been doing this show for that long. In the 1950s, we did an episode about the Cold War. No, sorry, about Jupiter's moons, and we put a lot of effort into the Jovian moons. We tend not to talk about future missions because they just get canceled
And explode.
and explode, and so
That Russian rocket was kind of amazing.
like we're you keep punting the Curiosity episode just because
I'm waiting for science returns, and they're starting to get them.
yeah. So that's it. So just like this is Pamela's level of conservatism. Now I am glad to do episodes about all kinds of speculative nonsense, but Pamela's the one who kind of,
It's
keeps
supposed
me
to be a
leashed.
facts-based
Facts.
show.
Exactly. And for example, like we haven't done an episode on James Webb, and we're just gonna wait till it launches and does its thing. We haven't done an episode on New Horizons yet.
And unfurls.
And unfurls
Yeah.
its beautiful telescope. And we haven't done an episode about New Horizons yet. Same thing. We're waiting. Boy, as soon as it crosses Pluto in 2015, we will be all over that. So I can't wait to see pictures of Pluto. It's going to be so great. We in the space journalism world, we have to use the same images of Pluto again and again and again. There's like 4 images of Pluto, and we just keep recycling them. I cannot wait.
There's a
actual
whole rest
photographs.
of the universe you can write articles on.
Yeah, but if I'm going to have to write an article on Pluto, I'm going to need that image.
You can use the image of the telescope that was studying Pluto.
Then what? Right? I'm saying we just keep running out. So, let's see. Any more questions? Andrew Planet says, find your antipode at antipoder.com. So antipodr.com. And I'm going to do it right now. I'm pretty sure it's in the Indian Ocean. So let me see.
Okay, I'm going to potentially jiggle my screen again.
Okay, let me see.
It's ANTIPOD.
Yeah, ANTIPODR. Yeah, so I am the closest landmass for me in Courtney, British Columbia, is like some little island, the French Southern and Antarctic lands. So I'm way south of, just north of Antarctica, sort of south of Madagascar, but way below Africa. So I am not going to visit there.
Mine is in New Zealand. I'm kind of good with that.
From home, but what about now when you're in Portugal?
No, from Lisbon. It's in New Zealand.
Oh, okay.
I do home. I should do home.
Yeah. Hope you're all doing this as well. You're also in the Indian Ocean.
Yeah,
Right.
we can see each other in the Indian Ocean.
Yeah, separated by 4,000 miles. Cool. Well, that's a great tool. That's awesome. I'm gonna share that somewhere.
Twitter.
I don't know. What is this Twitter you speak of? Randy8118 says, I'm more excited to see Ceres in 2015 than Pluto.
Me too.
Oh, don't
I
make me
agree.
choose. Don't make me choose. I cannot wait to see Ceres. Like, I'm totally stoked to see Ceres, more than Vesta, right? Because, I mean, this is on the other side of the frost line. What are we going to see? This is going to be neat. Because we knew Vesta was just going to be a big, another spud, right?
And
Pounded
the
up
thing is,
asteroid.
Ceres has enough gravity that you can almost imagine, like, eventually humans walking around on it happily. Not like, no atmosphere or anything, but it's moon quality, not too hard to get to in the grand scheme of things. Let's go hang out. And I'm excited about Ceres. I don't see us going to Pluto. It's an iceberg in the outer solar system.
Graham Stickings has a great suggestion for an episode, actually. These mathematical relationships prove Professor Marcus du Sautoy's point that maths is the queen of the sciences. Maybe you could do something on values that occur in nature, like pi, e, and root minus 1. And I think
Didn't we do something like that?
we did an episode on some fundamental numbers, like omega and
Okay.
and things like that, but we haven't done sort of some of the other natural. I don't know.
Yeah.
We should take another crack at it. I think it's a great idea for an episode.
And for those of you who don't already know about it, there's a fabulous video series called 60 Symbols that does this in huge detail. So we're
Yeah.
not going to replicate what they did because we can't.
No.
It's amazing.
Yeah. And they're way
But
beyond 60. I think at this point they've.
yeah, yeah.
Yeah. It's
So
fantastic. Yeah. Check that on YouTube. It's called 60 Signals.
yeah.
Um. Cool.
Symbols. 60
60
symbol.
symbols. Yeah.
It would be cool if we had 60 signals from somewhere.
From space. Space. Okay. Well, I think that's all the questions that I'm seeing.
Okay.
And I know that you're sleepy, so why don't we wrap this up?
And we
Um,
will be doing this again next week, although the week after is still questionable, so we may hide an episode in a random moment.
and in a random place.
Yes. Yeah.
Okay.
Well, no, it'll definitely be in Lisbon. I'm not going to do wild podcasts from Greece.
Are you going to be in Greece next?
Yeah.
Wow. Okay. That's awesome. All right, cool. So the next thing that is happening,
There will be a pre-recorded learning space going up on Wednesday.
okay, and then we're going to do the weekly space hangout on Friday
Yep.
at noon. So we do our roundup of all the big space news that happened this week with a whole pile of space journalists. So join us. It's fun. And then the virtual star party on Sunday night. So, all right. Well, thanks,
Sounds
Pamela.
good.
And thanks, everyone, for joining us today. Really appreciate it. And we will see you all next time.
Okay. Sounds good.
Oh,
Bye.
wrong. We're going to go into the inverse square law and other what did you describe it?
Nonlinear.
Nonlinear relationships. Which sounds like a dating site or something. Are you looking for a nonlinear relationship? I don't know.
No.
No, no. An exponential relationship. Right. So it's going to take us about 25 minutes to record the episode, and then we will wrap up and then stick around and try to answer some questions. Although it is evening for Pamela and she's hungry, so it better be really snappy questions. So if you've got some questions you want to ask, you've got some posts you want to make while we're recording the show, you can make your posts on the event page. Hopefully you're watching this there. If you're watching this over on YouTube, you can make a comment there. You can use Twitter, use the hashtag AstronomyCast, although the Hangout gadget we're using doesn't track that anymore.
Really?
So, yeah, so I have to I gotta look somewhere else now.
I can monitor Twitter.
Always do.
I like the Twitters.
Yeah. Okay, sure. On the Earth to find out where it would be. Great. So yeah, so you're in Portugal, continuing your European vacation, workcation.
No.
Yeah, I know it's
No.
totally not a vacation. You're working.
Yeah, my European inflict CosmoQuest on people in other countries.
All right. So the European tour, the CosmoQuest European tour.
Yes, that I'll agree with.
All right, cool. And I want to make one quick little promotion and mention, which is that every Sunday night we connect a bunch of telescopes into a live Google Plus Hangout and show you the night sky live in real time. We'll show you planets. We'll show you deep sky objects, clusters, the moon, the sun. Sometimes it's fun times, and we often will bring in PhD astronomers to explain this stuff. So if you've got cloudy skies and you don't know what to do with your Sunday evening, join us on Google Plus. We do it whenever it gets dark on the West Coast. Right now it's summertime, so that's 9 p.m. Pacific Daylight Time, and even later in the East. But it'll get better in the summer. So. All right.
It'll get better in the winter.
It'll get better in the winter. It gets
For
intro in front of me here. Hold on. Now I'm the one holding this
Sorry,
up.
Preston. And Preston, good luck working on your thesis. You have all of our hopes and cheers and chocolate wishes going towards you.
Aw. All right, here we go. Astronomy Cast, episode 312 for Monday, June 24th, 2013. The Inverse Square Law and Other Strangeness. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos. We help you understand not only what we know, but how we know what we know. My name is Fraser Kane. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. I'm almost as far as we've ever been apart doing an astronomy cast this week. Last week was further, but this week I'm in Lisbon while you're in Vancouver, so we're spanning the continents here.
We could drill a hole right through the Earth, and
No.
no, I think I'd be in the Indian Ocean if I drilled the hole through the Earth.
Yeah, I don't know where I'd come out.
Really? Um, you should figure that out. I think there's a website you can go and check out that is like your antipode. Yeah, and then
Sorry for the motion, everyone.
you're actually not moving from my perspective, but
Okay.
um,
It has image stabilization built in. Because, yeah, it's moving. There. Okay, I'm done typing. We're stable again.
that's weird. Is the image stabilization just like paused you entirely?
Okay.
Yeah. Anyway, okay, great. So, is there anything you wanted to announce, mention, exclaim,
Don't
complain?
eat in kebab pizzerias in Finland?
Bad tummy. Yeah, all right. I think we'll save that from the episode.
Okay.
Okay, great. Well, I'm gonna press record.
Okay. I should do the same thing, shouldn't I?
You know, it's one of those things that we do maybe sometimes.
Okay, I have pressed record. It is recording. The levels look okay.
I am also recording. All right. Oh, there we go. Hello, Pamela.
Hey, how are you doing?
Good. And where are you now?
I am outside of Lisbon, Portugal, in one of the suburbs.
That's really cool. And you've been there. And so what are you doing there?
I am here working with folks at Nucleo who work on the Global Hands-On Universe and the Galileo Teacher Training Program to find ways to integrate CosmoQuest into what they're doing to help get more people around the world using CosmoQuest.
So no vacation, all work.
Well, there will be some evenings spent walking castles and things like that. So it will be full work days, but it will also be full evenings, and I will probably return home in August, tired and thinner for all of the work, but having accomplished a lot.
That is awesome. I'm getting some echo here. Hold on. There, killed it. All right. Cool. So if anyone has no idea what they've stumbled into, we are going to be recording a live episode of Astronomy Cast. This is our weekly facts-based journey through the cosmos. So this is going to be episode 312.